Yo, yo, yo. What's up, what's up? Welcome back. Today we're working on my Rust operating system for x86. It doesn't do a ton right now, but we're getting a lot closer every day to something that like does something of value. Well, value. It can do something. So right now it boots, it has like memory allocation, it has like Rust async await support, it has like logging to like the serial console, which is forwarded in the context of a virtual machine to like my standard input output. It also like has VGA support, so monitor or the virtual machine window. And it has logging, unit testing. It can interact with the clock, so we can like do sleeps and use timers, stuff like that. And we have PCI, Ethernet, ARP, and UDP. So that means that we can look up an IP address and negotiate who to send a frame to, and we can like send and receive UDP. Last stream, we were working on our like proof of concept TCP setup. So we have now in this demo, if I like run the OS and I open netcat and I try to start sending stuff, I can like start seeing that these things are indeed received by my operating system, which is pretty sick. And if I look at how we implemented this, we have, hold on, where is it? It's like the way that we would use this implementation is pretty straightforward. So all we do is we like set up a listener, like a TCP listener that like opens. There's not really opening a socket in this OS because we're not really that high level yet, but we say, hey, we want to be notified when somebody talks to us on this port. When somebody connects to us and does their TCP handshake, we like get a connection, and we can connect. We can like wait for data from that connection and read data from it when we want. So that's all working pretty good. And so what I want to be able to do now is I want to be able to say, like let data is equal to the connection read. Like this. And then I want to be able to send it back. So I want to be able to say like connection.write data.wait or something. Right, so I just want to be able to make like a little echo server, I guess. So maybe we'll say today's goal is a TCP echo. There's a little bit of like, I made a little bit of progress off stream, so we got pretty damn close to that point. But we weren't quite there. There was just like a minor piece of like TCP negotiation that wasn't quite right. So the trick is we were getting our ACK numbers a little bit wrong. So what happens is in TCP, we have like the client over here, which is like the host OS for us, and the server, which is my operating system. And he sends a message over here, and he says like message with like data, like a sequence number, and I'm supposed to ACK back the sequence number plus like the data length. And we were getting that a little bit wrong, so I just had to do a little bit of double checking there to get it right. So there was a couple things. One was that the payload, hold on, somewhere here we have a payload, and here we were not correctly. So in our IPv4 frame, for context, we have Ethernet holds IPv4 holds TCP. Like this. And so what happens is this IPv4 frame was like a little bit, it might get padded with zeros by the Ethernet layer, because this guy needs to be greater than or equal to 64, but this might be a lot smaller, and this might be like smaller as well. And so what happens is we needed to make sure that we were only pulling out this part. So if we like have like our buffer like this, it was like ending here, but we were like returning all of this stuff as well. So that was the first fix, and then the second fix was just in the TCP section. We just have to make sure that we're sending Or when we increase our ACK number, we have to increment to. We were basically telling the client like, hey, this is the next byte we're willing to receive, and we were just we were doing +1 instead. So after those two, we can like receive multiple messages back to back. Very cool, very cool. And yeah, today I want to see what we would do to like send data over this TCP connection. So let's think. Yeah, I think that's pretty good. What the way this is modeled in the OS right now is we have like our like main loop over here, and he has like TCP listener. This listener, he like outputs TCP connections. Right? And this TCP connection has a channel under him to receive data. So he has like receiver. We'll call it RX for receive. And this is like a little like basically a expanding buffer, so like a queue essentially, that's connected to a TX buffer over here, who is connected to like our TCP state. Who is connected to the Ethernet driver. Oh my god, that's an these are awful. Jeez, okay. And over here, we also then run the Ethernet driver from main. So we kind of have like two paths here. This is connected to like, you know, if we go farther, this is like PCI. And back to CPU over here. So what happens is data comes in on the wire here. We run our our driver will like call a handler, and he'll like propagate data to TCP, propagate data to this channel, this bit's propagate over here, over here, over here, and we read. And so for the write path, we just kind of, or not over there, sorry, we are looking at this point. Maybe this, depends on if it's like a packet for an existing connection or for a new connection. And so what we want to add back is we want to add this write path where we probably, I guess, would have another channel here, TX RX. Oh gosh, RX. And we'd probably just want to add this like write path here where he goes up like this. And then this goes over to TCP, and then we have to probably instead, how do I say this? He at some point has to forward to Ethernet driver, but this will be like kind of injected from another path because the Ethernet driver won't be polling TCP because he won't be like receiving any data, but we will want to write data. Easy peasy. Yeah, so that's probably where we're gonna go with that. And I think we can probably just start jumping in. So this was 0847, and then what's our next step? Add TCP write. So there's a bunch of like state handling that's gonna have to happen here. Like we're gonna have maybe how is this? We have to like handle retransmission in this case, right? Like if we send something to the client, the other side, and they don't receive it, and we have to actually handle that. I've been like reading TCP spec, and there's a lot of stuff in there that I don't understand, and there's like actually like fairly complex things like congestion calculation and like trying to manage like how much data should I send before I start like giving up, how long do I have between connections, stuff like that. And so I think what I'm going to do is I'm going to start with something simple. So I'm just going to like poke and prod until I get the behavior that I want. And then maybe we'll go back and try to like actually implement TCP spec. So we're going to acknowledge right up front that what we're implementing is like wrong, right? We can just say that right now. And we'll learn how it is shit by using it and seeing where it goes. Yeah. Okay. So let's get moving. So the first thing we want to do is add in this like write API, right? And so we're gonna go to this read function in our TCP connection, and we're just gonna add a write guy. And he's gonna write, what is he gonna write? He's gonna write a buffer. Is it a slice? Is it a vec? Probably it's gonna be an owned buffer, because this has to be propagated over to the Ethernet driver asynchronously, and we don't really want to deal with lifetimes and all that. Maybe. I was going to say, I might be wrong. Sorry. Let me think. So there's a couple options here. One is that like our TCP connection just like immediately writes the data. And that means that he would have to own a reference to our Ethernet driver in order to like send the packet out. That's option one. So let's look at this. Option one. TCP connection owns reference to Ethernet driver. Option two is that TCP connection generates a packet that is fed to the Ethernet driver. Option three is that the TCP connection how do I say this? Dispatches the TCP connection like waits the wrong word maybe. The TCP connection what am I trying to say? He forwards data to TCP subsystem that is serviced by someone else. Or four, TCP connection forwards reference to TCP subsystem and does not drop until complete. Right, so this, when I say TCP subsystem, I'm talking about, right now we have this like TCP section and he owns all of the like states of TCP connections essentially. So the like sequence number and ACK number and like port pairs and stuff like that, that's all kind of owned by this like big TCP struct. And so the question is like, how do I want to get my data over there? So this, in my mind, is like the easiest, most obvious implementation to me. All I would have to do is I would like replace it with like a self tx write data, if data was a vector of U8, right? And then somewhere else, like that's it in terms of the connection, right? Because then someone else could service the TCP system whenever it needs, and it would just like propagate automatically. Now the downside of that approach is that we have to like copy the data into the TCP subsystem, and that does kind of blow, right? Like a better option is if we can, in terms of performance, is if we can do this, right? And if we have that, then we don't have to copy the data in, right? But then the problem is now this is going to go out of scope at some point, and we won't know when. Another option, actually, a much simpler option, is if instead of this being is a vector or a slice, we could actually make this an RC U8. And if we did that, then we have this like shared pointer to a slice of data that's never copied, right? We're going to do cheap pointer copies to copy it around, but it's reference counted, so it won't go out of scope until everybody's done with it. And that might be nice. The only question is I don't know if it's expensive to generate one of those. So let's just double check here. So if I look up the docs for RC, he takes a value in and he consumes it. I don't know if this is like, I don't know, how do I say this? I don't know how expensive that is to generate, right? There's obviously APIs that are being worked on to handle working with slices of data, right? Like the fact that they're saying like new on-init slice is like an API that is being worked on, and that you like write the data in manually after, that really makes it seem like there's performance implications of trying to copy this data in. But that's fine. Let's, I guess, let's see if like the box version has something. Like I just want to know, like, how do I heap allocate an array? That's all I really want to know. Maybe we can say like Rust heap allocate array. I guess you would use the vector constructor and convert it, I bet. Right, so the vector constructor, I think you have this like pretty efficient macro here to generate the data. Sorry, to like to initialize heap buffer. And then you can probably convert this into like an RC by going like, do we have just RC? We have it into arc, we have it into RC. Yeah, so this definitely is something that can be done. Okay, sure. Can we, I guess the only question is if we wanted to initialize something like hello world, I don't know if we can like make something like this. Oh, but that's okay. So all of this to say that I think that this is an okay API, and it would also be okay for it to be this. And we can just enforce that callers, if they're going to use data this way, like they can, how do I say this? They can choose to not copy it if they don't want it, right? Easy, easy, easy. And if we want to get really crazy, and the caller already has this as a vector, you could actually write this as like something like this, I think. And you could say where t is from or into, I should say, into RC U8. I think you can do something like this. And then you can call data.into. And then here you could have this as like a tx is sender RC U8. Something like that, right? And really, maybe we should be giving it the same treatment on the receiver side, right? Like all of the same rationale for I'm not gonna copy the data, I'm gonna copy a reference to the data, right? All of that kind of like lines up. So maybe we should do it that way everywhere. But for now, we'll just start here and see where we end up. Okay, so we need the RC type, which means that here we need to go RC, RC. There's no method write for sender in the current scope, so it's just send, not write. In main, they don't like this, so here this should be data t, right? And now I think in main, like this concept of sending in this data that's evacuate and converting it into RC, I think all that just like comes for free, which is kind of nice little API there. Now we have these like TCP connections that we construct somewhere, and we need to now give it a TX as well. So we have to make a new channel again. So this is going to be send. We'll rename this to receiver TX, or like TX in, I guess we can say, and RX in. So these are like incoming packets, and then we can say let TX out RX out is another async channel. Like this. And now he takes in TX out here. And someone needs to hold the reader end of that. And so that's presumably the TCP subsystem, right? So let's think about this. We actually might be able to get away with... I was going to say we can get away with only having one receiver. But that's not true. These receivers have to be associated with a TCP state, which means that each TCP state probably has a RX on it. Receiver RC U8. Right? That probably makes sense. So once we're connected, we are allowed to send data. Great. And now here we have RX is RX out. Very cool. And what happens now is probably our TCP subsystem. He's going to like accumulate buffers that are meant to go out, and we're going to have to service that somehow, right? So probably what we're going to do, let's just delete all this shit that we don't need anymore, is we're going to have like a pub async function service. And he's going to take in our Ethernet driver. No. I was going to say he's going to take in our Ethernet driver. And the reason to do that is so that he can send data out. But the way that our abstraction is set up is that we want our TCP subsystem to not need to know how to package up the surrounding frames, right? So we have like this setup where we have, you know, this like Ethernet frame, IP frame, TCP. And we want like the TCP subsystem to only care about TCP stuff. And so probably what this guy's going to do is, this won't be called service. We'll call this like, no, service is fine. And what this is going to return is it's going to return like a bunch of packets to send out. Right? So this is going to be data that he wants to wrap in IPv4 frames and Ethernet frames and send out to the network. So he's going to say the packets that we want is a vec new, right? And then what we're going to do is we're going to iterate over every single connection that we have, right? All of our TCP states. We're going to iterate over all of them. We're going to look at them and we're going to say, did anybody try to send a packet? And if they did, we'll generate it and we'll add it to the list. You could also maybe argue that this should generate one at a time, right? Because if these are expensive to generate, if like people write like lots and lots and lots of data, you might want to like just pop these out one at a time so that you're not like pre-allocating way too much data at once before you're even setting it out. So maybe we, instead of doing a vec of vector, we do an option vec u8, right? And that means that if we have a packet, we return it. Otherwise, we don't. It would be nice to have like this future, like a stream that you have in like, how do I say this? In like stream from, in the futures crate, I think, they have these like stream types, where you have this like, I'm going to get the next one and the next one and the next one. I can do like a 4x and y kind of thing. And I was going to say that this would be kind of nice because it would mean that we can have like efficient lookup without having to like recheck a bunch of stuff that we're not looking at. But I think that the way that this would work is on each poll, you would look for where you have data to send, and that kind of sucks. That kind of sucks. So I think we don't really have a choice but to iterate over all of our listeners or all of our receivers of data every time. Which is fine. I think that that's probably pretty cheap. Cheap enough for now, right? Like in high performance networking, we would not want to do this, but we're doing proof of concept. So we can iterate over where are our receivers located. They're in these like states. So we'll say let TCP states is equal to self TCP TCP states lock, right? Now we have like a mutable thing that we can look at. And then we have TCP states. So we iterate over all of them. For state in TCP states. Then we try to receive something. So we can say state dot r. What is the type of this? This is a, what the fuck? I actually don't know what that is. That's some crazy type. Do I have to like do a and star here? There we go. So our state is a TCP key, TCP state. So probably we can do like values. We don't care about the keys, I think. I was going to say we don't care about the keys, but I think that's actually a lie. Because an important part of the like TCP packet that we need to send is like a checksum that includes the like remote and local IP and port. And those aren't included in the state itself. They are only included in the key in the hash map. So we actually do need to iterate over all of these. And we can say for TCP key and TCP state in this guy. And probably I don't have to dereference him actually. Oh, maybe I do. Weird. And what I can do is I can say, is there anything ready? So I can say TCP state, which I think it has an RX in there. Does it not? Hold on. TCP state. I thought I just put one in there. Oh, this is only for connected states. So we can say match TCP state. And we'll say that we have like a connected state here. Right? And the connected state will be the connected state if it is it. So we'll say, what is this? TCP state connected. And if we have this, then we just propagate it on. And anything else, we just say like, fuck it, we can't do this. And we'll continue the next iteration of the loop. Cool. So now we have this like connected state. And in here we have an RX. And this is of type receiver that we wrote last stream for like an async receiver. And a problem here is that we don't have a way to like check if there's something here. We only have a way to like block forever. And so we actually just have to write like a try receive function that takes a option T. And what he does is, let's think. So the first thing he's going to do is he's going to try to lock the mutex. And I think that we can say that try receive locking the mutex for the data is a reasonable thing to do. It can't check unless there's data in there. So we'll make this an async function that does try to lock the mutex, but he will not wait for data to actually get in there. So he'll just say self.inner lock await, right? So we have the guard here. And we will have this guard and we'll say this is like a queue inside, right? We have this like mutex queue. And so all he has to do is he has to check if he can do anything else. So we can just say guard pop front. And if this is ready to go, then he'll get some data. Boom. Nice. And so we should probably just like do another test here where right now we're testing the async channel with only the blocking version, but we can test the try version as well. So let's just copy paste this same test and we'll test the try version. So instead of doing this receive poll trick here, we're just going to say we put some data in. The first thing we do is we're going to try to receive, and that should fucking give us someone. And if we do this again, it should give us none. Okay. And do we compile? We do not compile. There's all sorts of things wrong. So one is that I actually broke some stuff last night when I was trying to do this. So this should be total length is 20, or header length should be 20, I think. And this test EQ that I just threw in here, he gets mad because he doesn't know which type of none this is, so we can just say, I actually don't know what type this is. This is an I32. I hope so. Yep, there we go. And we got close. So it actually turns out that the changes I made to make TCP work is creating IPv4 validation issues. So let's just see where those come from. So probably there's a bug with the total length here. Yeah. And so we'll just write a fix me here. Maybe broken UDP parsing, question mark? Okay. Okay. So we now have this like try receive function. So we can go back to our TCP thing. And in here we can, for each of these states, we can try to get some data. And if we get some, what are we going to do? We're going to generate a TCP tap packet and return it. So we're going to say return self. What are we going to say? Generate TCP push, I guess we'll call it, and we'll pass in the connected state because that's important. We'll probably have to pass it in as mutable because there's going to be a chance that not a chance. We're definitely going to have to like update our previous sequence number. So every time we write something, we say like, I sent sequence number 50, and now I've sent sequence number 55, and I've sent sequence number 60. And we need to like keep track of what we sent. And there's also going to have to be later some sort of like buffering of sent things, because we can't delete the data until we know that the ACK has been how do I say this? We can't delete it until we've got an ACK from the other side, because we might need to resend if there's been drop packets, etc. But we're gonna handle that later. So we're gonna give it the connected state and the data. Okay. This needs to be an await. And we need to now create this function. So that'll probably go on here. So mute connections. Sure. So this is the connection state. And we're also going to take in the data, which I think we said was a bar C U8 or slice or something. And the output of this is going to be a Beck U8, I guess, probably. And we'll say this is unimplemented. So what doesn't he like? This needs to be wrapped in sum, of course, because this is a failable thing. And we need to borrow this data. Cannot borrow connected state is mutable, so we have to just write mute on here. And is there a problem here? Hold on. So we have this mute connected state. What is this connected state? He's and connected state, because this is not mutable here. This now also needs to be mutable. Do I have to write this and mute if this is mutable? Maybe not. So much lifetime / mutability issues. So this cannot be borrowed as mutable. Right. So why the fuck not? What are the types here? So connected state is an and reference. So I do probably just have to write and mute here. So let's look at this again. Do I need to write mute here? No. What is he mad about? Let's just cargo check again. So this is a connected state, and I can't force it to be mutable here. Aha! I have to write mute here. Perfect. No, it actually still is not right. What the fuck is going on? Oh, probably this needs to be mutable, which means also this needs to be mutable, which means this already is mutable. And if I look at the type here, that's a mute connected state. Perfect. That took forever. It's hard to reason about sometimes. But now we've got the right types with the right mutability. And we already know that the TCP key here is relevant too, so we'll just pass this in as well. Like this. TCP key and TCP key. Okay. Okay. So I guess we could argue that we have like TCP write API implemented, and what we're trying to do now is actually send the TCP frame. And so this is at like 3644. Easy. Okay. Okay. So how do we generate this TCP push? So what do we have? We have this function generate TCP frame that takes in these params. So clearly all we're going to do is we're going to generate some specific TCP frame and return that up. Bing, bang, boom. And now the only hard part is figuring out what the fuck goes in here, right? So we have TCP frame params. Now, let's just start copy pasting this shit and filling it in. So source address, this is easy. This is TCP key local IP. Guest address, also easy. TCP key remote IP. Source port, easy. TCP key local port. And the destination port is the remote one. Sequence number must come from the state, right? The ACNUM also must come from the state. The flags are going to be TCP flags. How do I generate these again? There's a... Aha. Generate TCP flags. There's... Generate TCP flags with TCP flags params. So what goes in this guy? Oops, this guy needs TCP flags like this as well. Okay. So probably the only thing that we're trying to set in here is ACK. I think if I remember the spec correctly, most of these guys are nothing. So we'll put false for everything. And we'll say we always need to put the ACK in here, so we'll do that. I think I read that in the spec somewhere. Window size, I don't know. I think I'll just write 512 there and see what happens. I think that this is part of like congestion control is where this is supposed to come from, but I don't have any of that, so set this to something sane. Our urgent pointer is always going to be 0, and our payload is just going to be the data. Wow. That actually seemed a lot more reasonable than I thought. So here, we do this, we do this, and now the only thing that we need to do is we need to increase our sequence number. So we are now going to bump it up by the size of our TCP frame plus the data, I guess. I think that that's what it is. The sequence number, I believe, well, we can just check on the other side. Here, not here. Here, we increase the ACNUM by the payload length. So that's actually easy. We don't have to keep track of the header length of TCP. It's actually just payload length again. So here, before we return, we just say state.seekNum. It just is increased by data len, as you do. And yeah, that's kind of pleasantly surprising. That might be all there is to it. Really. Okay, so now from main, we are going to have some sort of like TCP sender loop, right? And what he's going to do is he is going to look at the TCP shit. He's going to try servicing him, right? And based off what we just did here, sometimes if there's some data to write, he should get some data back. So we'll say if let some data is equal to this. This is actually going to happen in a loop. Right, and he's going to get some data, and if he gets some, he's going to try to send it. So he'll say, let IPv4 frame is equal to net generate IPv4 frame, and it's going to be based off of the payload that we get here. So this is data. The protocol is going to be IPv4 protocol TCP, and the source IP and dest IP are not logged here. So getting just the buffer back here isn't sufficient. We also need to know which key this is associated with. So the question here is TCP key a public type right now? And do I want it to be? Right now, this is kind of like internal data to like our TCP subsystem. And is it okay to just leak this out? I don't really see why not, but I don't know if it makes sense to. I'm also, yeah, I guess I'll just leak the IPs themselves. So on this service function, we generate a buffer and we also generate data. So this is actually going to be something like struct outgoing packet, outgoing TCP packet, right? And what this is going to have is it's going to have a local IP, which is a IP address. It's going to have a remote IP, also an IP adder, and it's going to have a payload, which is a vec u8. Cool. And so now this is not going to be an option vec u8. This is going to be an option of outgoing TCP packets. Outgoing TCP packet. And here now I have to say like let payload is equal to this. And let ret is equal to outgoing TCP packet that has a payload of payload. It has a local IP of connected state or TCP key, local IP, and it has a remote IP of TCP key remote IP. Easy. Easy peasy. Then we just return the ret. Bing, bang, boom. Easy. Okay, so now this is the outgoing data. And this is outgoing data payload instead of just the data directly. These all need to be public so that we can access them externally. And And the last thing we have is now we have to like punch these guys in. So the source IP is outgoing data dot local IP, and the other one is outgoing data remote IP. We stick some ampersands in here so that the compiler doesn't get fucking bitchy about us. What's it bitching about now, though? It's still... We need to await this. And we need some borrows. So this needs to be an ampersand as well. Cool. Now we can generate an Ethernet frame from the IPv4 frame. So here we say net generate Ethernet frame. The params are Ethernet frame params. And what goes in here? This stuff. Okay. So the MAC addresses, the destination MAC comes from our ARP table. So we can say self.arp table.wait for dest MAC. Now this gets a little tricky because we actually have to like generate our ARP request and send it out if we're going to do this, right? So what happens is we have an IP that we're associated with, and we want to send data to that IP, but on the Ethernet layer, IPs don't exist. And so what we do is, what we're supposed to do is we're supposed to say like, hey, anybody know where this IP is? And then somebody will go like, oh yeah, that's me. I'm MAC address this guy. And so we have this ARP table that tracks those in like input and outputs. And then we have this way to say like, when I get that data, like look, or when I get somebody else's MAC, like tell me what it is. Sorry, outgoing data remote IP. Now the problem is what if we have never issued this request? We don't actually know. So we should maybe do that. But you could argue that in our case, since we are working with a TCP connection that already exists, we should already know where this is. There's a good chance that's wrong, and if it is wrong, then we'll just hang here forever and it'll be really obvious. So let's try this, and maybe just sort of fix me. It says like generate ARP request if needed. And in here, we'll probably put like automatically try ARP resolution. I think that'll probably be necessary at some point. The source MAC comes from our Ethernet driver, so we just say get MAC like this. Our Ethernet type is IPv4, and the payload is just the data that we got. Okay, and then we just send that shit out. So we say Ethernet driver, write this Ethernet frame. And do we have to await this? We do. Sick. And we'll just for now write unwrap here, because if it fails, then we should crash and we should try to debug. This will eventually be fixed because I use unwrap as a way to flag to myself that it's like, this is temporary testing code and we should not commit it like that. Okie dokie. So in here now, this now becomes a join all, and we pass in this third TCP service feature. And we probably have to pin it, or else Rust will be like, oh no, the data might move, and like, oh, my references will be invalidated, fuck. But if we just write this, then it doesn't do that. Now someone's bitching. What doesn't he like? What doesn't he like? Oh, so this join all of a sudden needs these to be type erased. So what happens is we have like an iterator, and the iterator has to have all of the same type. And what we have right now is we have 3 different distinct features with 3 different distinct types. And so, but they all implement the feature trait. So I think that there's like a way to just say like boxed from this guy. who lives in like this futures crate, which basically just like turns them into the heap allocated async or like dynamic version of them. But actually, I think you actually don't even need that. I think that we can just like convert these into references. And it might just kind of handle it all for us. Cargo check. So what's he bitching about? Maybe I write dyn here. Let's try to figure out this syntax. So let's see. I think if I do receive as dyn future, is that legal? Core future like this. Output equals this. Nothing. Okay, so that's legal, which means that or maybe, sorry, let's try one more. This should be a pin mute dyn core future output equals nothing. So what's he mad at? Oh, that's not bad at all. Oh, so we have some like type issues here. So this needs to be public for it to be part of the public API. And weirdly, this is the only thing that we needed to mark, because now these guys automatically get converted into the right types. That's kind of cool. I didn't know that that's how it worked. Okay, I guess we can just run it. Weirdly, I think that like we're kind of in a state where we can try and see what happens. So the fact that we've just hung here is a pretty good indicator that we fucked something up. So let's just take out this like new code that we added to the TCP service. And so that's a really good sign that basically something in our TCP service loop is hanging. Something in here. And that actually makes a lot of sense because we're just hot looping in here, right? And so I bet you if I like put a println in here and we say let mute I equals 0 and I plus equals 1, I bet we'll see this just being like, yeah, hot spammed, right? So what's happening is there's never anything to like, how do we say this? Rust futures, they do like cooperative multitasking, right? And so basically you stay within this future until you have something to block on. And if you don't have something to block on, then you will just never ever give up to let somebody else do what they need to do. And so what happens is we try to run this and we just get stuck here and we never handle these guys again. Gross. Bad us. So what you would normally do is the problem is like the core of the problem is this guy, right? We made our API say like, hey, check if there's any packets to send out. And if there aren't, we'll just go again. And what we should really do here is we should, in this call, we should wait for any of them, right? Not this like try receive that we implemented is actually bullshit. We don't want that. We actually want, we want to like collect all of these readers, wait on all of them and pick the first one. So I think that's like something like, we do TCP states. Sorry, I need to restart my editor real quick because the language server is not working. I'm not getting auto-completion, which is a disaster. Okay, so I think it's like TCP states. And we can like run this as an iterator. And for each thing in the iterator, we can map it to Okay, I was gonna try to do like the like method chaining way of doing this, but that's kind of harder than just doing it this way. So instead, I'm gonna say let mute connections is a vector, right? We iterate over all of these guys, and if they are in this state, we say connections push connected state. And maybe we do it like this. Then, well, what I'm trying to do here is I'm trying to like make a list of futures to wait on so that we can wait on them all at once. And when we wait on them all at once, we'll just get the first one that finishes. But that's like maybe not super trivial. And so what I'll do instead is I'll say fix me wait for one of many. And in our main loop, we'll just kind of like inject a sleep in here. Just to get away from it. So I think this is sleep dot await. Our time will just like service it like every like 0.030 milliseconds. And then we need to pass in our monotonic time and wake up list. So this is like just some tracking variables that we have for when to wake this feature up. And now if we run this, this is happening much slower and our actual other parts of the kernel are running. So we can delete this print line and this tracking variable because we know that we're running correctly now. And what we want to see is we want to see if when we connect, we send something. Holy shit. Wow. I really didn't expect that to work. Like at all. That's fucking crazy. Okay. So what we expected to happen was that we receive the data and we send it back out, and nobody like is needing retransmissions or anything. Yeah, that's sick. So what's happening is we're bouncing data into our OS. The OS is like receiving it and bouncing it back out, and we're getting it. That's fucking sick. Wow. Okay. So here we're actually going to say that we succeeded at TCP echo server, and this was a success at 5810. Okay, wow, that's nice. So now we can start trying to like collect some of these fix me's and fix them up a little bit. So one of these things that we want to do is we want to like automatically handle ARP resolution, right? We're like just asking for problems with this ARP frame, or sorry, with this like ARP table not having the data that we need. And the other thing we wanted to do is wait on fix TCP service await. And I actually want to do that first. So basically I don't want to have to like pull this in the future. That's like fucking stupid. Instead, we should have this await setup that we were trying to set up like maybe like 2 minutes ago. And let's just think about what this is. So so we're going to want to map the outputs of these futures, right? These, like this receive here. We're going to want to map this to the stuff in here. So we're going to say connected state .rx.receive. And can we just call map on these futures? Yes, we can. Fuck yeah. So because these like the futures crate has this like super sick module, which is futures X. We basically get these like ways to like interact with our futures and like automatically do stuff, like kind of like chain dependencies. So we can say like once we get this thing, then transform it into this thing and wait on that. The other way you could do this is you could create async functions that do it imperatively, but this is kind of like a nice little cheat here. Is it? I'm actually down to still do it this way with the async function. So we'll say async function. We'll say received packet. No. Write request. That's what we're getting here, right? We have like our TCP connections, and we're saying like, does somebody want to write from those guys to the outside world? And we'll say, well, this is a write request to outgoing packet. And he takes in something. The request is a RC shared reference to a U8 array, slice, whatever you want to call it, on the heap. And this is just this, right? And he doesn't have to be an option anymore. And he returns a outgoing TCP packet. And he doesn't just get the request, he also needs the key and the connection state. As a mutable reference, actually. This is data. And we can use this as like a U8 slice directly. This guy doesn't need this. And are we close here? We are close. Okay, here we go. So this function compiles. And now we can say, write request to outgoing packet. Hey, what's going on here? We are trying to write a TCP echo server. So we have an operating system that we're implementing, and we have got to the point now where we can like connect to it from our Linux host with Netcat. We can like send stuff to him, and he's like correctly parsing the TCP data and like handling TCP state well enough so that he can like read the data and understand what it says, as well as send data back without messing up like TCP handshaking. We're pretty far from like actual reliable data transfer, but we are at the point where in our perfect virtual network, things are working. And so now what we're trying to do is we got to that point with like a couple hacks that we weren't really too happy with. One of which is what we're working on now, where we're trying to basically we were like polling the state of our TCP section to say, hey, is there any packets to send? Hey, is there any packets to send? Hey, is there any packets to send? And we kind of want something like a little bit nicer that instead of like spamming it every 30 milliseconds, it will just automatically wait until there's something to do. So we have this like TCP async Rust shit, and we're just trying to like collect all of our incoming, all of our like write requests into like one thing that we can wait on. Yeah, that's where we are. So for each of these guys, we are going to try to wait for him. And if we wait for him, we're going to... this is going to be like an async block. Did you make your own Tokyo? It's very rudimentary. Here, we'll pop it open. So this right here is the entirety of my version of Tokyo. So I like take in a feature, and all I do is poll it, and if it's not ready, if it's pending, I just halt the CPU, because we're like in a kernel. We don't have to like worry about anybody else trying to do anything. We don't like what you would normally do in like a real operating system is you would like forward this data. Sorry, forward data. You would like context switch to another process. But instead of doing that, we just turn off the CPU because we're like, fuck it. If we don't have anything to do, nobody has anything to do. And what happens is like when data comes in on the Ethernet card, that'll trigger like an interrupt that will wake the CPU up, and then we pull the features again. So this is like something that's like analogous to Tokyo, but I'm sure Tokyo's is much more feature complete, if that makes sense. Yeah, okay. So what were we doing? We were trying to say how are we going to like propagate this state? So we're gonna like get the data, and then we're gonna call this function we just wrote, which was write request to outgoing packet, and that's takes in the TCP key, the connected state, the data. And probably we need some like borrows. So realistically, you would have something more like yield to the kernel. Yeah, exactly. Instead of that halt, you would have like you could just write like like if you would use like a condition variable. Probably that's what I would do. Is I would have a mutex in a condition variable, and when somebody like gets a signal from the OS, they would post that condition variable, and that condition variable says like, hey Linux, could you please break up this process again? And then he would. But instead we just halt the CPU. We need to borrow this guy. And what doesn't he like? Returns a value referencing data owned by the current function. Okay, so we can, luckily for us, since this is a shared reference, we can kind of just do an RC clone data. And then I think that nothing is referenced by the current function. No, it is. Fuck. What doesn't Rust like here? Cargo check. So he's saying that because we have data borrowed here, we can't use it. So is this one of those like async move things? No. Fuck. I guess we could take this in by value, and probably that would fix it. So if I like go here and I take this in by value, and I remove this borrow, does that compile? It's close. We need to borrow here. Oh, I'm an idiot. I forgot to await. If I just awaited here at the beginning, it probably would have been fine. So I do type await here. Nice. Nice, nice, nice. So we can say, here we have a feature that will like pull the data from this specific connection. And if it gets something, then it will return to the caller. Great. This guy doesn't have to be async, so there's no reason to write await here. And we can say let future is equal to this guy. Okay, can I delete this now? Yes, okay. So now I have a future for this specific connection. And I can put this into a list of connections for all of our list of futures for all our connections. So we could say let mute futures is equal to a vector, probably. We'll push this into the futures vector. And then we'll just wait on all of these at once. And we'll just return the first one that finishes. So we can say futures, future select all. And here we'll return our future. We'll stick in all the futures that we want to wait on. And I think we can just like await. And almost certainly this is going to bitch about something. So let's see. One is that these have to be pinned. So how do I pin these guys? I think I can do like iter map core pin. No. I think I have to type boxed here. So this will push this future onto the heap, unfortunately, but it will handle like the pinning to make sure that it's got a static memory allocation, and I'm just willing to take that hit for now. And now it doesn't like that we are not returning the right type, so this select all call in the futures crate is what they're called. It basically says like, I have a bunch of things that I want to do, and I'm gonna give back the first one that worked, and I'll also like give you back all of the unfinished futures as well. But I don't care about any of those. I only cared about the one that worked. The other ones we will regenerate on like a future loop. And now I think that this compiles, but no, it does not. We have a lot of problems here. What do we not like? Jesus, this is a lot of errors. We were close. So first, let's clear up this guy in main. So before he was saying if we get some data, and now we don't have this like if we get some data. We're always going to get some data. So we're saying let data is this TCP service shit. We delete this loop. We back these off at indent level. And I need to fix the name of this guy to outgoing data. So from main's perspective, we're happy. We're ready to go. Now here we have all sorts of problems here. So it's all probably, there's two problems here. One is that there's an expectation that we can send this between multiple threads, which is not true because of the mutex guard that we're using is like single threaded. I think that there's like an easy fix here with this like boxed thing. There's boxed local and boxed. So one of them just expects that it's pinned to the heap and shareable between threads, and the other one I think just is that does not require that. So if I write local here, that fixes one of my problems. But there's all sorts of other warnings that are coming here due to like lifetime management shit. So let's read the longer errors. TCP states. So we lock this mutex. And we use it in this iterator, and then we use the data that we pulled out of that iterator in these features. It doesn't like, for some reason, that this guy lives so long, or does not live long enough. Where does he think that this is going to be part of? Where does he think that this is going to be used? Oh, this is weird. They're saying that I can force it to be dropped. Oh, that's weird. I've never seen that before. No way. So let's just try with that recommendation, and if it works, then I'll kind of explain it a little bit further. Cargo check. No way. Okay, so what I think is happening here is when we created this TCP states thing, he is going to try to get dropped when they're finished with him. And when they're finished with him is when this guy finishes being run, right? So when we pull out this like .0 here, the other parts, which are like the parts where this guy is like contained in the other features, they will be dropped as well. And if we try to drop that like at the end of the block, like directly, like you normally would with Rust, it actually doesn't deallocate this guy or drop him until after the return, and then that it like gets angry. But if you just do this, then it's okay. That's very strange. I've never seen that before, and that's because like it will get dropped here instead of here, one line before. That's crazy. That is crazy. And I need to actually allow whatever ClippyLint is bitching about this, because Clippy's like, hey, you shouldn't do that. Why wouldn't you just return it? And it's because there is a subtle difference that it's not thinking about. Okay, so let's run this and see if we still work. So, no. No, we don't still work. That's sick. So, where is this assertion? ret.inner.isEmpty. How do I find where this is? Is empty. I actually don't have that assertion anywhere that I'm aware of. That's kind of fun. That's actually really fun. So we can probably assume that it's caused by this service loop that we were just working with. So unfortunately, I have no way to like debug well inside my OS right now. So we're just gonna have to like do some commenting and running and seeing if that helps. So let's first start by just commenting out all of this, and I think expect it to still crash, which we do. If I comment this out, I guess if we just don't run this feature, we should expect it to not crash. Great. So we are fairly confident that it is this code we were just writing. And I guess we can... let's think. Instead of running these futures, let's just return a futures future... What is it? Pending? So we'll just block on this forever. And write unimplemented below here. So if this doesn't work, if this doesn't crash, then all of this is okay as long as we don't like actually run them. What doesn't it like though? It doesn't like that it can't infer the type. So we'll just say like this. Okay. So that's we're narrowing in, right? We now know that this line specifically is where the crash is happening. What we can do is maybe we can await here instead of pushing the future into this array. And if we crash now, then there's a problem with the actual future itself, but that's not it. So it might actually have to do with we create this future that does some shit, and we take him out of this scope, and it could actually be that we are losing some important data. So, not losing, like maybe it's using a reference to some data that isn't existing anymore, and that's crashing in some way that we didn't expect. Specifically, maybe it's related to this ref counted data. So I would actually like to try just doing what we were doing before, but try not doing anything with the data. Let's not try to dereference this reference counted pointer. Let's just run, see if we can like pull the data out. And so that actually doesn't work either. Does this work where we do nothing? Oh, that's interesting. So I was going to say, what was I going to say? I thought that it was related to some of our code, but it doesn't seem like that. It seems like it's related to something to do with this select all. So, or maybe it's to do with the box local. So let's try, instead of running this select all, for now, let's just say for fut in futures, fut.await. Right? So now this like bisects the fact that this select all is doing something stupid. Can't I print to QEMU? Yeah, that's what I'm doing right now. But like it's hard to, I don't have like back traces or anything fancy like that. So I'm only capable of like printf debugging, which sucks, right? I'd rather, if I was a little more motivated to fix some tooling, I would way rather be like in GDP right now. But we're not there. Or at least have like my panic statement print a backtrace. Okay. So it looks like the futures themselves are actually good, and there's a bug in the select all implementation, right? Because this unimplemented is getting hit now, right? So if I said like return here, cargo run. Yeah, I know. I'm sure that there's like a way. Let's look at what this crate is. We're kind of in this situation where we are like using our own linker script, and I don't know if we have like dwarf info, but this is promising. Backtrace support for no SDD environments. Yeah, it's not crazy. Definitely something to look into. But for now, I'm gonna keep being lazy and keep doing this stupid way. Why is this not working? Return fut.await. Oh, we put stuff to write unimplemented here. Okay, so if I run this, not implemented. Oh, it's probably just bugged when it's empty. So if futures, I see. So if we have no connected TCP sockets, we actually just won't we won't have anything in these features, and that causes a bug because I bet you if I read the documentation for select all, it probably says that I have to have at least one element. Yeah, right here. This function will panic if the iterator specified contains no items. Okay. So now the question is how do I wait in the case where I have no connected TCP sockets? What do I do? And I guess what I do is instead of just continuing, I just push a feature into this vector that will never return. I can just say futures.push futures future pending. I think. We'll try that. And then there's also this case where we are doing nothing. And so actually we should have at least one already in here. And that way we will always have a valid vector or a valid iterator. But the ones that aren't connected won't do anything. That seems reasonable. Cargo check. This is not alloc vec vec. We need alloc normal vec. Or sorry, just single. And we need this to be box local as well. Okay. We're close. We're close, we're close, we're close. This expected pending found pin box local. Oh, because this guy also needs to be box local. Jesus. Are we done yet? Okay, nice. Okay, so we're running. Let's connect. Test. Okay, so maybe we're still hanging somewhere. Let's just double check. So we run our operating system. We try to connect to it. We say we received an IPv4 frame, and then nothing interesting happens. So probably we're hanging again in our TCP service. So let's take a look at this. So let's do the easy thing and just disable the TCP service loop completely, and we should be fairly confident that we will go back to working there. At least we're receiving data, right? Sorry. Let's log that we're receiving data so that we can be certain. Here, we should say we received some data. So let's just double check. Why? Oh, here we go. Yeah, here he is receiving data. Test, test, hello. Why is he not receiving it every time? That's maybe a bug. Yeah, that's interesting. It's not working every time, so there's a bug somewhere in there as well. But it should be running back as well. Okay, so let's go back into this. Let's add back our TCP loop. Oh, I'm an idiot. It's because here I'm trying to read a second packet, so I'm only printing every other one. So we'll do it like this. Okay, cargo run. Let's see if we are getting the data now. Test, test, test. No. And so we can be pretty confident that this TCP service is doing something fucking stupid. So let's just do this like sanity check where we see if we're just spamming the loop again. So spam I, let mute I equals 0, I plus equals 1. And we will see now if we're just like spamming, like this loop is just never yielding. No. Interesting. Interesting, interesting, interesting. So we're actually, top of screen is cut off. Is that true? On OBS, it looks okay to me. On Twitch, is it broken? Let's see. I think I'm seeing everything. Scroll up. Yeah, I mean, I think on my page, I'm seeing my whole screen. So I think it's okay. You're seeing it too. Huh. I wonder why it looks okay. Oh, is it because I'm like, there's no window border on this guy? Is that why? You just think that there should be a title bar up top or something? Yeah, not sure. Anyways, let's see here. So this TCP service is actually never getting into this loop at all. I didn't see this print line happen one time. Oh, I did see the spam happen once and just never again. Interesting. So that just means that this outgoing data is probably never returning. That would be my guess, my like next guess here. So we can check that. We can say so we can just print another thing here and see if we ever get out of that. So here we connect, we send some data, and yeah, we're never getting into that section. So that's interesting. Thinking. How do we bisect? So this is wrong. Although that shouldn't make a difference. Cargo check. Cargo run. Was it related to that unimplemented block? No. No, it is not. Which makes sense, because we would be crashing if it was unimplemented. Interesting. I'm confused, because I don't think that this should change anything. Really. Like, I have this, like, pending shit, but that shouldn't matter. Right, because what should happen is, we should still at least receive the data on our, like, handle TCP connection side. But we see if we delete this section from being run, if we just don't run the like that echo server loop, I think we do see the data. Hello, hi. Yeah, right, that's like coming in. So what am I missing? Is this open source? Yeah, all of the code is available on github.com/spheraphoria. What's it probably called? StreamOS. Yeah, this is where it is. We don't have like the TCP stuff in yet, but it'll be coming. I try to push fairly frequently, so it's a little behind, but most of it's in there. Okay. So why the fuck does... I would think that the TCP data would be visible. Oh, wait, hold on. Okay. I think I understand. So in my service loop, I bet I'm locking this mutex, right? And I'm locking this mutex and never returning from here, right? Because I have this like pending state, and while I'm waiting for this is locked, which is fucked. I can't... And so then when I try to like actually handle an incoming TCP frame, I try to lock the mutex again, and I just hang forever because this is never returning and this is still locked. Okay, so how do I get out of that state? How do I get out of that state? I guess we just can't... We can't do it this way. We can't have futures that will not resolve quickly. In fact, what we should do is actually each of these futures needs to lock this mutex individually and like skip forward to its element, which is actually possible. So what we can do is we can actually keep track of the keys instead of the receivers, I think. And is there like do I have like a try lock method on this guy? I do. So could I like try lock, and if the lock succeeds, then pull the data out or something? And if it doesn't, just return? No, that's not what I want. This is complicated. We're starting to get into the territory where like maybe I would like add a future here that I manually chain all of this stuff in. So I could say like struct outgoing polar, and this guy might like keep the TCP key inside him, and or then what would happen? I would like lock the mutex, look up this one thing, try to receive. If I receive, then continue. If I don't receive, drop the mutex. Which seems reasonable, actually. This actually might work. So I don't know if I can do like an implementation of a trait inside a function body like this, but let's see. So I'll implement future for outgoing polar. And we implement the poll function. The output here is going to be a outgoing TCP packet. And on poll, we're going to start getting crazy. We are going to... we also have to keep a reference to the TCP states, which is the dictionary of like all of our TCP connections. And he actually has like a more complex type. This is it is a mutex guarded hash map TCP key to TCP state. Okay. So this is taken in by reference. And so now this guy contains a reference. And so on each poll, he is going to try to lock this mutex. So he'll say let guard is the self.tcp states.lock, and then we'll poll this. With CX, the context that we've passed in. We probably have to pin this guy or else somebody's gonna get mad. So we go like this. If this succeeds, we're gonna have this is poll ready. We'll propagate them. Otherwise, this is poll pending. Just say we like return poll pending. We are not ready. We have to use core task poll. So here we just shove this guy in here. Okay. So now we have like a locked thing very temporarily, and then we'll say guard, let's think here. We look up the connected state receiver. So we say guard dot get guard. What is the type of guard here? It should be a mutex guard of a hash map. Yeah, so the hash map should have a retrieve function. Is it add? Get? It's gotta be get. So we try to retrieve the connection for the TCP key. Oh, I spelled guard wrong. That's why it's bitching. And get returns like an option, so we'll just unwrap here because I don't want to deal with the option stuff. And then we can try to get the data from this. So we say this is match this guy dot receive, and we have to do the same thing where we call the pin version poll of this. And if we have poll ready, we return it, we propagate, otherwise we return pending none, or that we're pending, sorry. And if we have the data, then we can do this. And we also need the connection state. Great, where does that come from? That's just connection. Okay, so if we do all of that, and then instead of doing this, we just shove our own future in there. So we just say outgoing polar. Outgoing polar. And this we convert into a box local, and we say TCP key is TCP key, and the TCP states is self.tcp states. I wonder if this will work. There's all sorts of things that it's going to complain about. So let's cargo check and just try to start working through errors now. 497, not in scope. So here I probably just used the wrong word. Connected state should be connection. Cargo check again. I've got the name of this struct wrong. So here I wrote down the name wrong. Where'd it go? Down here. Too many L's. We cargo check again. We need to clone this guy here. So this guy I'm passing in by reference, but I need to pass him by value. So we'll just copy like this, or maybe we'll write clone on him. He's gonna bitch that he doesn't implement clone, so we'll add that to his implementation. Where is his implementation? Clone. We cargo check again. TCP state doesn't have args received because TCP state, where was I? I got lost again. So because this TCP state could be in many states, the only state we care about is the connection state. So if we're, or in the connected state, so we'll say let connection equals match connection. And if we are in TCP state connected, we propagate. Otherwise, we say we're pending. Now, this is kind of weird, but I think that this matches the behavior we were trying to implement before in the imperative version of this function. Maybe imperative is the wrong word. In async block function version. Okay, so now we are actually pretty close. We just need to throw a couple ampersands on here. This needs to be mutable, which means that probably this guy needs to be mutable. And now we just return ready here. All right, okay. Cannot borrow is mutable. Fuck. So this connection, I'm just gonna quickly restart my editor because the language server seems to be broken. And try to find where we were. So this connection is of type TCP state. So this just needs to be a get mute probably, which means that this has to be mutable. And now this guy can go away. We don't need this anymore. We don't need this anymore, or we do, but he can be here. We can drop him down here so that the mutex gets unlocked before we actually do any polling. And maybe we're chilling. That compiles. Okay. Does it run and do what we expect it to do? That's looking good. That's looking pretty good. We're not blocking forever anymore. We're still not getting our echoed data back, which we expect to. So let's just double check that we have everything hooked up the way we want it. So here it's because we're not running the TCP service. So we actually don't know if it's working yet. Let's try again. TCP service. What have I got wrong here? Found the async block. So it expected, oh, I need to pin it, that's why. Stupid pinning. So this is core pin pin. And if I pin it, then the future is runnable. Come on, moment of truth. So let's test. Oh, hello. So we're still not getting the data back. Oh, fuck. Why is this so hard? But at least we're not hanging up the whole world anymore. So that's a good indication that our mutex strategy was in fact correct. I guess the problem is maybe... No, I don't know. I don't have a good guess. I thought I would. So we had this log spam1. Spam2 never happens, which means that we never return from this on the first iteration. And that actually makes sense, right? Because on our first iteration, there are no valid futures. And so we'll actually end up returning this like pending version of it, and we'll wait forever. And we don't want to wait forever. In the case that there aren't any items, we probably actually just want to like sleep for some amount of time and then check again. Now, obviously, we're back to this like sleep shit show that we didn't want to be in. And so that means that probably we need to have some sort of way to like async wait on a TCP state being added. Blech. Gross. I'm deciding that I don't like any of this, and I'm just going to go back to the 30 millisecond sleep poll version of this for now, because this is like turning out to be less clean than I thought it was going to be. I thought it was going to be cleaner to wait correctly. And so I'll just have to like revert back to what we had about like probably like 30 minutes ago. Yeah, okay. So is that easy to get back to? I probably forgot to commit. Yep, I definitely did not commit that as a checkpoint. So let's just kind of like go back by hand, I guess. So I think it was pretty easy. I think we had this guy returning an option of outgoing TCP packet. Okay, well, before I get crazy, let's just quickly throw in a checkpoint, because it's almost certain that I'm going to mess something else up. So this was returning an option here before. And then we were looping through all of our TCP states. And if one of them was valid, we were returning an option. So we said, this guy was here. And we would return true, or return some in this case. We were checking if we were in the connected state. So here we were saying if we were not connected, then we just continue to the next iteration of the loop. If we are connected, then we're good to go. This is not self dot anymore. This is just TCP key. This is data. So this data comes from the args received. So we were doing like a self dot or connection rx receive dot await here probably. We were doing a try receive here. And we were saying like if we got something here, we were gonna use it, otherwise return none, or we continue. Sorry. So this is probably where we were before. Here we would return none if there was none. And I can just delete all this shit. Okay. Wow, that was actually a lot easier to get back than I thought it would be. So then back here, we were saying if let some... If there was data, from the service, we do all of this shit. Otherwise, we were sleeping for like 30 milliseconds. So that's the self.monotonic time, self.wakeup list, and these need to have ampersands behind them. Okay, please, please, please be back in a working state. So cargo run. Okay. There we go. Okay, we're back, baby. So, okay. Cool. We're gonna add a checkpoint here. And I really wish that this isn't how we were doing it, but that was really turning out to be really ugly, so I'm okay with leaving it this way for now. And we're kind of at the time where it doesn't make sense to try to do more. So I think I'm going to call it there. Anybody who's watching and is enjoying what we're seeing, you can always catch up on YouTube if you want to see more and you miss it live. The YouTube is linked in the Twitch description. And if you're watching on YouTube and you want to say hi, you can always pop by on Twitch at like most days around 2 Pacific. Just to do a quick little recap, what we did today was we looked at TCP echo survey. We like doing a TCP echo. So we already had TCP receive, we were getting the data, and we just kind of like hooked up the pieces to write that data back to the same TCP stream. And it actually didn't turn out to be that difficult. We then explored the idea of like trying to do a little more future-y Rust code, and that was like a little more rough. And we kind of like experimented there and decided that it wasn't worth it at this point. So thanks for watching. This was fun. Catch you in the next one. Bye.